Alright, everybody, welcome back. It's been a while, so I appreciate the patience. It's been quite a busy time for me. I've had a lot of projects going on and learned a lot of stuff that I'm excited to distill and share with you guys over the next couple months. So without further ado, let's get into it today. We're going to look again at Vertex shaders. In this case, we're going to be looking at a Vertex shader effect inside of a feedback loop that will allow that feedback loop to, I think, look a lot more interesting and dynamic than a lot of the normal, completely top-based feedback loops that we're used to seeing around. So a little bit different for this one. I've actually got this effect built out pretty completely, and this is probably going to be a multiple part tutorial, but I wanted to give everyone the full file now at the beginning so that one, you can see kind of where we're going, and then two, so that it's a little bit easier for me to illustrate some points. Like for example, one of the things we're going to be looking at is how to use the Vertex shader to fix an optimization problem and really speed up our program. So I have that already built so that we can take the short route for some of this stuff and focus on the more interesting bits for following along. So, with all of that said, we can jump into things. This project file is available on my Patreon. For anyone who is a member there, feel free to grab it. If not, you can head over to patreon.com /water_shed and pick it up there. All right, so what is this effect? Let's take a look. Essentially, we have a feedback loop. That feedback loop is being composed of two layers. There's a fluid simulation layer, and then there is this triangle mesh distort layer, which we can kind of see what's happening there. And we'll get more into that in a second. These two layers are basically composited over top of each other, and that composite is then what is fed through the feedback loop to generate this effect. So we're going to go over each of these in part, as well as the chops over here that are kind of driving some of the animation. But first, we can just take a quick look at what the effect can do. So here we can turn the feedback up or down. We can add fluid to the feedback effect or not. So here we're adding a ton of fluid and a lot of feedback. Here there's just fluid, no feedback. And then I'm just messing with the color here. So if we add some feedback back in here, we start to see this come together. Now, the other thing that I'm sure you've noticed is this countdown that's bouncing around in the middle and kind of generating this fluid. That bouncing is, again, something that we'll look at easily animating. It's super simple, but really that text is meant to be anything. So this, we had a text here, but, oops, there we go, text. It could be anything, so we can just replace this with lake, for example, but it also doesn't really have to be a texture. For example, if we use our classic banana, we can see the same thing starts to work with our banana. And so, as I'm sure you've noticed, if I turn the optical flow off, or sorry, well, I just gave it away. If I turn the feedback off, it's pretty clear that there's some optical flow going on here too, since we're only really generating motion when our subject is moving. Okay, so that's kind of the overview of the effect. We have this bouncing image that is passed through an optical flow. That optical flow is used to generate some fluid or other effect. I'm just using the fluid here. And then all of that is passed into a feedback loop that includes some vertex shader based rendering, and that's what we're about to look at right now. So here is our vertex shader rendering code. Now this looks slightly messy at the moment, and that is mostly because I have two things built here, and we really only need one of them. But I wanted to have them both built to illustrate, again, the point of using the vertex shader. So this is really the meat of what we're doing, or actually, I guess this is really the meat of what we're doing, and that is simply taking a grid, triangle grid, and perturbing that grid quite extensively, and then rendering our image on top of that perturbed grid, and then just comping that render on top of a feedback loop. If we go back here so that we can just kind of see everything at once, this also gives us some interesting things to play with in the feedback loop. So our displacement, by turning it up or down, really changes how things look, and the smoothness. There's also this exponent, which we can kind of see adds a little bit more depth and darkness. We'll see exactly what that is doing in a second. Turn the displace weight the whole way up. We can make the scale translate faster or slower. And then one of my favorite things is adjusting this period here. And so with like a high weight, high period type effect, you get some of these cooler like kind of color block things. If we translate that a little bit faster, again, just some pretty cool effects, and this is just really scratching the surface of what we can do here. All right. So now that we've kind of went over what the effect is, we can take a look at the first part of this series, which is going to be looking at just the vertex shader component. So even if I just take out this completely, I think, well, I guess I can't just take it out completely like that. But if I instead just replace this with a constant and have that constant have an alpha of 0, so basically now I'm just, it's not really going to work nicely, is it? Okay, that's fine. I wanted to illustrate a point, but I will make it later. So yeah, the first thing we're going to do is focus on this triangle mesh distortion component, because this is the main piece that's using vertex shaders, and the rest is frankly pretty self-explanatory. I think this is the key here. So what is going on in this effect? Here we're using a grid. This grid is just a polygon grid with alternating triangles. And like I said, we're distorting that grid. Now, we're going to distort it in two ways. First, we're going to be distorting it with a SOP chain, which is decidedly not the right way to do it. And then we're going to be distorting it with a vertex shader. So this, right now I'm using the vertex shader texture, and we can see that it's running Pretty light, not crazy. 0.2 milliseconds on the GPU and about zero point 0.3 on the CPU. Now, if I flip this over to using the SOP distortion, you can see that our effect looks very similar. I'm going to turn this translate down a little bit. This distortion looks very similar, but we are now running at 6 seconds on the CPU and still just at 2.2 milliseconds on the CPU. So we can save ourselves like a crazy amount, like I don't know, a 85-ish% reduction by using a Vertex shader to replicate this this effect. Okay, so yeah, I'm just gonna delete all of this. Fuck it, we'll set up something real quick. Um, so yeah, deleting all of this and starting from scratch. First, I will grab an in and get my feedback back here. Then I will just take it right to an out, and there. Now our feedback network is going again. Now this is obviously not too much of anything going on here. So what I will do is start our grid. So I will drop down our grid. I have these parameters, which I think everyone is pretty well aware of how to create at this point. So I'm just going to keep these created as parameters. Feel free to create your own as you're going along. So my grid res here, I'm going to drop onto my rows and columns. I'm going to make it a polygon with alternating triangles. Open the viewer, turn on wireframe. Now I'm going to want my grid size to be the same as this texture size. So we can say op in 1, or actually no, this x size can be 1, and then we can do op in 1 dot height over op in 1 dot width. And now our grid is aspect corrected, like it should be. Now do a null, and I'll insert an attribute create and turn on my normals and tangents. Then I'll middle mouse click. I will drop down a geo. I will add a wireframe to this geo at the moment, and then I'm going to add a camera and a render and a in this case I think just an ambient light. You can see the render is starting to work here. Now we also want our render to be the same resolution as our input, so we can do this op in 1 dot width and height, like that. We can do a 16-bit float render, and then we can output that render instead of our input. Now we just turn our cam to ortho and make it an ortho width of 1, and this we can verify gets us with this grid snapped exactly to the outside of our now aspect corrected viewer. We're going to get rid of this wireframe and instead add a null map. and then a constant mat, which I will wire into the null. We'll call this null mat just mat, and then drop it on here. I'll add a null after my in1, and we can call this color, and then I'll drag that color onto my constant. And now we can see that we have a simple recreation of that feedback loop. There's not really any difference between me just dragging this in1 out to the out directly versus passing it through this render. So this is kind of the abstract layout of what I think is a very powerful procedural workflow to be able to start designing your own very nuanced and also customizable feedback loops. Because now anything we do to this canvas is going to be added into our feedback loop. So just something easy would be if we add a noise SOP. Just like that. And we can see that this feedback loop, or sorry, that this canvas is now being distorted. If we come up a level higher, seeing that there's not a ton of distortion that's visible right now, and that is, I think, because of our orthographic canvas. Okay, actually I take that back, not because of the orthographic canvas, possibly though because we were using a render material that doesn't really deal with normals and tangents, so we need a Phong that will allow us to get some of this specularity in there. And now we can see that this texture is indeed being distorted. It's just not that obvious, and the period of our distortion isn't that high. So it becomes a lot more obvious if we do something like that, and we go back to ortho, but I guess in this, it actually kind of looks a little bit better with the perspective view because we're doing z-space. Anyway, we don't really want to do this anyway because this noise is not very customizable and will take a long time to cook the bigger you get. So another way that we could add some distortion is by just using a noise chop, and to do that, we can use this noise chop. We can use an info, drag this grid onto the info, and then we can look at the number of points. So we can take our number of points from this info and use that for the number of samples in our noise. And we'll just do -1 because we're zero indexing. Now this noise period we want very small. And then what we can basically do is just take one for ty, one for tx, change the seed, merge these two together, and then taking that same expression for tz, we can just do a constant pattern of amplitude 0 and give it the same length. And then we can call that TZ. And so now we have our XYZ coordinates. And then what we can do is use a point SOP and actually use this position. And each input point has something called index. So now, if I do a null after this merge and call it distort, I can look up distort channel TX, and then I can grab the sample that's going to be the index of the point. And so then if I just do that for TX, TY, and TZ, you see that this distortion is much more apparent. And that distortion continues if we're on an orthographic camera. That's because we have this distortion going in the X and Y, but not the Z directions. But it looks pretty distorted right now. I'm going to open up these parameters again and use some of the parameters that I have to, one, create the period, and then two, the displace weight itself. So now we can make these no displacement. Oh, although that's not actually exactly what we want, because that will make our position 0 when our displace weight's at 0, and we don't actually want that. We want our position to be at the grid position, so we'll fix that in a second. But then this period, we can also drag and drop. So I guess this is probably the issue. It's that we are using the distortion as the position, but we should really just be adding the distortion to the position. So we can do input point, input point, and I think it's X, like this. Yeah. So these are grabbing the attributes that the 3D engine is giving to the geometry before it's being passed into the SOP. So basically the attributes that the grid SOP is putting on geometry when it's created. And so we can grab those input points and then simply just add this distortion to it, which allows then when we turn the weight to 0 to have an undistorted canvas, and when we turn the weight high to have a very distorted canvas. So if we have this distortion weight very high, it's one thing, so it kind of all moves them away, and I think that's because why is that? We can look maybe SOP to dat and look at what our points are actually doing. A little distortion like that is a little bit better. So when we're going really high, we're not actually moving these things away. If we look here, we can kind of see that our central point isn't changing. What we're seeing here is instead the fact that we have some alpha on the outskirts of our image, and so when we're distorting it with a super high displace weight, those transparent sections are just kind of being like spread over the whole view. So when we have a lower displace weight, things look a little bit better. Now, this isn't running too crazy at the moment, but it's also not looking super interesting at the moment. And that's because we want to translate this noise. So I already have some parameters. These parameters are called color translate scale and position translate scale. The color we'll come back to. We'll just use the position translate scale for now, although I'm going to use both of them. And what we're going to do is use those constants with this speed. And I'm going to do a rename, and I'll rename this to CTX and C speed and T speed, like that, and a null. And what I'm going to do is use this T speed to translate the noise chops here. And so now we get this motion. And then by increasing this speed, we increase our speed of translation. I like using this format, this constant into a speed, as a way of translating instead of using like abs time. Sorry, instead of using abs time, because it allows you to scale the speeds more smoothly, and also doesn't require you like hard coding a bunch of abs time expressions. Okay, and then the other thing, although this is already, I think, looking a lot better, and we can see the feedback effect starting to take shape a lot more now that we have this displacement in motion. One of the last things that we want to do is possibly be able to take some selective triangles out of our grid and turn their color off. Make them transparent, so that we kind of have like some holes in our feedback that can lead to some pretty cool, interesting dynamics. So we can't use point color for that, or a point SOP. We need to use a primitive SOP because that will let us change the actual primitives themselves. So we'll add color, and then we'll change this input alpha. Now, the way that we'll do that is by using another noise chop here. And I'll call this color noise. And here we'll change our channel to samples. And we'll grab the number of primitives. And then again, -1 because we're zero indexing. Now, I'm going to move it down here. These buttons, by the way, are all courtesy of Function Store. He's got a cool component that will add this toolbar that gives you a ton of cool functionality and just buttons that make workflow a lot easier. So, yeah, we'll get to that in a second, I guess, but I may as well take my color speed and start to translate using the color speed, because that's the whole reason that I have it. and then I'm going to turn that period way down. Now, here we just want to apply this to our transparency, so I'm going to add a function. I'll make that the absolute value. Then we can add some gain or something like that. And then we'll throw it all down and we'll call this alpha. And I'll put a limit right before that, and I will clamp at 0 to 1. And now this primitive, we can change the alpha. You can use op alpha like we're used to, and then I guess I'll change that channel to A, and then we'll want the sample from me.input_prim.index. Since we're not using a point, we're using a primitive. And then I just need to change this channel to A. And now we're using this alpha noise to change the alpha primitive by primitive on our render. So if you go back here, I turn my displace off. Then we can start to see where some of this comes in. I guess maybe it'll also be more clear if we have a background like this. So no transparency, no translating the color a lot. And then we can see the effects that this might have on our feedback loop, although we need to do a couple of things to make that obvious. First, this is pretty chaotic. There's a lot of movement and stuff. I want it to be a little bit more subtle. That is what this color exponent is for. So maybe I'll change that range to something like 10. And then we can see that we can just use this exponent to really fine-tune kind of how many transparent tiles there are. So I'll put that way up, which means that there's not very many holes. And then we'll turn this translate down. And actually, I think I want it like really high. And if putting it at, let's say, 10 isn't quite doing it, we can use this gain to get a lot more. Okay, actually that gain isn't doing a ton because of our clamp and because these values are so tiny. So actually, it'll help a little bit, but it won't do a ton. Excuse me. And this one is a very expensive operation. So now we're running, right around that 6 milliseconds. Get our displace weight up there. So we've got the cool effect, we've got some of this feedback going, but we're running at like 7, almost 8 milliseconds right now for that part of the effect. And that is not something that we're really going to want to deal with. So what I'm going to do is take this Phong shader, and basically what I've done so far is I've done this in SOPs, which I think is helpful because one, it's interesting to see what you can do with SOPs, and I think it's good to know about things like the point SOP and the primitive SOP, and how you can use them. But it is not super great from a performance perspective for all things. And those things, when it is not going to be ideal from a performance perspective, is when you're doing an animation on every part of the geometry at every frame. That's almost never going to scale well in SOP world. So anyway, what I'm going to do is copy and paste this Phong. I'm going to output these shaders. And that is going to give me a new Phong GLSL that I can use as a material. And that way, we can use our Vertex shader to do a lot of this in a much more performant way. So to make this a little easier, I'm going to add a switch. And then I'm going to add a switch here to my materials. And now I'm going to drag and drop this toggle that I already have, and actually I'm going to make sure that the GLSL Phong GLSL is the first input. And then I'll do the same here. So now, when this is off, we're using our Vertex shader. Oh wait, whoops, this should be like that. Okay, so when this is off, we're using our Vertex shader to render. So here we're just rendering the grid itself. And then when this is on, we're passing this grid through this pipeline. And we're using this original Phong material. So we can put these up here. Okay, so what do we need to do? Basically, all we need to do here is take our Vertex shader and apply turbulence inside of the Vertex shader. And then we can also apply some coloring inside of the Vertex shader. So I will edit this, bring it over here, and increase. Okay, so this is the Vertex shader. Again, nothing new here. I'm going to add a uniform, and sampler 2D will be the type, and then I'm going to call it S-turb. Then I'll just go to this sampler, I'll call it S-turb, and then we will want a noise top for that, which I will drop a null down after and call turb. Now for this noise, we'll make it not monochrome, 32-bit float, say, I'm going to leave the resolution as is for now, and then my amplitude can be 1. Well, really, I suppose my amplitude should be the same as this amplitude, my displace weight. Okay, so then in our vertex shader, I'm going to flip this so that we're using the vertex shader for rendering. So right now there's no distortion because all we're doing is basically applying a default Phong to a grid with nothing else. So not a ton that we need to do here. We can just call a new variable vec3 new p equals p. And in this case, p is a attribute that is coming in from the geometry. Then vec3 turb equals texture std 2d inputs. Actually, no, that's not right. Turb. And then overt dot text chord 0 dot st dot rgb. And so this is using the text chord from the vertex to look up the turbulence from our noise texture. And then we just say new p plus equals turb. Although I'm going to do just rg for now, or maybe forever. And then we just have to use new p there instead of our old p. Now we can see this distortion is occurring here. Kind of as you would expect. We can give ourselves some animation by using the same animation parameter. And then we can start to see in our feedback, if we displace nothing, we have no real feedback. But then as we increase our displacement, we get this feedback effect that starts in earnest and is working again. We're also back to running at our 0.2, 0.3 milliseconds on the CPU. And yeah, that's also just a lot easier, I think, than adding turbulence this other way. Like it took us, all of that work, versus one top and one line of shader code. So yeah, that's that for adding turbulence in the Vertex shader. And to alter the color, you can do something that is also pretty simple, especially for the transparency. Vert.color.a equals 0. And then we can see that we are adding transparency back via our vertex shader. So maybe we will just take a different noise. Have a top called alpha. Add this as a sampler. So S alpha. Go back to our vertex shader. Just copy and paste this line. And instead of it being a vec3 turb, we'll make it a float. and we'll just call it A. We'll just grab R, and then we'll use, A to set our overt color. Now we'll use this to be an exponent of 0 and an amplitude of 1. And don't think that's quite working. Aha. S alpha. And then I think we need to just add S alpha up here. And then, okay, so now we are adding in those specks of transparency. And something handy that we can do is click on this this little extender thing, and we can actually look up our filter and use nearest pixel filtering, which will give us a bit of a tighter clip, and add these splotches of transparency over our texture. So now, obviously, changing the period is going to change where this transparency comes in at, and how it looks. The exponent will also change that. So, yeah, that's just something else to play with. And then those transparency, we can use our transparency amplitude to then be able to toggle that. And then we can use this translate scale, or rather, we can use this color translate speed to transform our alpha. And so there we have basically all of the working pieces. Although I think this should be 1 minus, and then this offset should probably be 1. No, okay, so that's not quite right. Offset 0, exponent, whatever we want. Make it an 8-bit. If we look at this, okay, that's 0 to 1. That's great, but what we want is for our alpha to always be 1, and then for it to not be 1 otherwise. So we can use a constant, pass this in, and then change our noise to output input minus noise. Now when our amplitude is 0, input minus noise, why isn't that working? Aha. If our exponent is 1, then yes, our amplitude will now be subtractive. So, almost. There you go. So now a transparency amplitude of 0 will give us no transparency, and the transparency here is coming from the texture itself, not from our shader. And then if we have this transparency amplitude is higher, we actually are adding transparency through our shader as well. Cool. So I'm gonna stop here for today. I think that is a pretty good overview of how vertex shaders can be helpful. So now we're running that entire computation, including transparency and uh, transparency and distortion, and that whole thing is running at zero point 0.3 on the GPU and zero point 0.3 on the CPU. A lot better than our 7 or 8 milliseconds the other way. So that was the main takeaway from this tutorial. I do think that I'm going to be picking this up again to do another iteration, probably about optical flow, and maybe some of higher level ideas. But I wanted to get this first one out because it had been a while since I had done kind of a longer form tutorial, and I think that understanding when and where to use SOPs versus thinking about Shaderland and how those can complement each other and the best use cases for each is very important. So I will stop there. I want to thank my Patreons again. This has been a pretty incredible year for me as an artist and a person, and I don't think that any of that really would have been possible, or definitely not as easy, without the support of this community letting me basically be able to take the jump and also giving me a lot of support along the way. So I thank you all very much, and until next time.